Good afternoon, everyone. My name is Jung-Eun Chu. I'm an assistant professor from School of Energy and Environment at City University of Hong Kong. And it is my great honor to deliver a first talk in these meaningful occasions. So today I'm going to talk about how and why climate change intensifies extreme weather events. So we have been observing increasing number of black warnings and then also tropical cyclone warning these days. And currently from Hong Kong Observatory, there are 21 warnings. And then it can be divided into typhoon-related, rainfall-related, temperature-related, and some others. So maybe this can be a major extreme event occurring in Hong Kong. But globally, extreme weather event is defined as an unusual and rare event in space and time that encompass drought, heat wave, floodings, tropical cyclones, wildfires, and so on. But let me start by introducing a bitter February in 2021 in the United States. In 2020 December and 2021 January, during 2 months, entire United States experienced much warmer conditions than normal. And some of the parts in the north, they experienced about 10 degrees Celsius warmer than normal conditions. But in just 1 month later, what happened was that temperature drops dramatically about minus 10 degrees Celsius, and even during 2 weeks of the peak period, the temperature was about minus 15 degrees Celsius lower than normal. So if you consider the temperature difference, it's about 25-degree drops in just 2 weeks. But before that, people were saying that it's common to have a warm winter. So winter will be like that under the global warming condition. But sudden drops make a huge impact on people. And especially this event generated a huge and a severe cold wave event in the southern United States, in the area called Texas, where the temperature and climate is relatively similar to Hong Kong. Can you imagine Hong Kong have this kind of snowfall everywhere? We don't have snow chains, right? Same is true in Texas as well. So this generated power outages for more than 10 million people. This graph shows a satellite image of Texas, Houston before and after the snowfall event. So you can see many of the places are under the darkness. And then there were no electricity for more than 10 days. But this means that for 10 days, you cannot charge your phone, or you cannot charge your phone for communication or even asking for a help. And then also you cannot turn on the heater to warm your body in this freezing temperature. But at the same time, because the street was blocked by snowfall, no snow chain, no transport. So that's why people are suffered from shortage of food, water, and essential supplies like toilet papers. And then a lot of water pipe was broken at that time. So it was a huge humanitarian crisis. What happened during this time, meteorologically speaking, it was associated with a negative phase of Arctic oscillation and disruption of polar vortex. So typically during the winter, normal days, Arctic temperature is so cold and the mid-latitude is relatively warmer. And because of strong gradient, strong differences in the temperature, they generate the very strong jet stream. And then because of this jet stream, it traps the polar air in the Arctic region. And then mid-latitude can be protected. But for some reason, if Arctic becomes warmer, the temperature difference between Arctic and mid-latitude becomes weaker, and that weakens the westerly jet stream as well. And then that allows the polar air comes much downward, and then tropical air much upward. And that is exactly happened in Texas 2021. What about Asia? Asia is not exceptional. So this figure shows the temperature trend in winter time during last 30 to 40 years. And as you can see, Arctic temperature has been warmer much faster than other places. But at the same time, ironically, global warming increases cold event, especially in the middle latitude. So this, due to the melting of Arctic sea ice and snow cover, that amplifies the frequent negative phase of Arctic oscillation that weakers and weaker westerlies. So that's why more extreme middle latitude events occurring in the middle latitude. But Hong Kong is located in the subtropics, but we are also influenced a lot by middle latitude, especially during the winter time. So we are also not free from this event. Currently, everyone knows that global temperature has been increased globally. That's why it's called global warming. And then global mean temperature has been increased about 1.1 degrees Celsius from industrial revolution. But if you look at last 30 years only, temperature has been increased much faster than before. And if you look at the pattern, there are some characteristics. Land area has been warmer much faster than the ocean. And an Arctic region has been warmer 2 to 3 times faster than the remaining places in the world. And if you look at the temperature nearby Hong Kong, in Shenzhen, it has been increased about 1.6 degrees Celsius. So they are not equal. Global warming is a global phenomena, but the temperature increase is not equal. And especially these changes, these differences in temperature influence the weather pattern and then pressure, wind pattern, and that actually influenced the extreme weather events as well. I'm going to revisit it later. So because of global warming, currently every year we are listening about record-breaking heat wave, right? This place, other places, it becomes so common to break the record. But record is a record. Why it should be common? So this figure shows the heat wave record during last 6 years. And for example, here in Vietnam, they experienced 44.2 degrees Celsius warming. And then in Australia, it was higher than 50 degrees Celsius. But also, if you look at Canada, much further north, in 2021, the record was about 49.6 degrees Celsius. If you look at the graph on the right side, you can clearly see that heat wave has become more frequent, longer lasting, and then more intense across the globe. And this is a direct consequence of climate change. But what drives a heat wave? Heat wave can occur anywhere that high pressure system develops over a large area. For example, high pressure means that you have more air above you that pushes the air downward. So high pressure pushes air down toward the ground, and then if air sinks, it warms by compression. This is simple physics. And heat wave develops as this kind of weather pattern becomes stagnant, remain in the same place for longer time. That heat builds up over numerous days. And then that builds up kind of heat dome that traps the hot air inside of the dome. But scientifically speaking, the heat wave is defined as a higher temperature, higher than threshold for more than 5 consecutive days, where the heat threshold is typically 5 degrees Celsius lower than climatological temperature. But what makes the heat wave more dangerous is that when it's coupled with soil moisture. So we have learned that high pressure system increases temperature, but when this high pressure is formed over the land, over the high soil moisture area, because atmosphere is warm, the soil moisture will be evaporated into the atmosphere, and then soil become relatively drier. And then instead of evaporating, they transfer the heat in the form of sensible heat flux. That transferred heat is accumulated in the atmosphere. And then soil will lose more moisture as time goes by. So it will be more accumulated and more accumulation. So there is a kind of vicious cycle in heating up the atmosphere. So that's why many of the heat waves are coupled with drought event as well. Are we actually observing globally? Yes, there are evidences about it. For example, this one is a global trend of global mean temperature, surface temperature, and then here is the surface air relative humidity. So as you can see, together with the global warming trend, the surface humidity has been decreased, which means that we are having more dry conditions in the atmosphere. And then this graph shows the trend of soil moisture during last 50 years. And as you can see, many places in the world, like Eurasia, Southeast Asia, eastern coast of Australia, where most of the people are living, and then also a large area in Africa, and then west coast of America, like California, those having a decreasing trend of soil moisture. So we are getting more drought event. But speaking about the California, do you remember a massive wildfire event in California early this year in January? This generated more than 10 times size of Hong Kong, this area burnt by wildfires. But if you look at this graph, this is the total acres burned by wildfire. And then as you can see, there is a kind of slight increasing trend. And then gray shading is when they are coupled with a drought event. For example, from 2012 to 2018, there was a prolonged drought event, and then the total area burnt by wildfire has been increasing. And by the time, it was a record. But 1 year later, it seems like stopped suddenly. But another problem is that 1 year later, in 2020, there were record-breaking wildfire happens. And then that burnt more than 4 million acres of the area burned by wildfires. What happened in 2022 was relatively similar to what happened in 2020. It was a typical compound hazard. Compound hazard means that occurrence of the multiple hazard at the same time or consecutively. So what happened was that before this drought event in 2025 January, there were very unusual wet period for almost 2 years. And during this wet period, abundant growth of grasses and bushes occurred. And then this became a potential fuel for fires. And at the same time, the fuel does not necessarily mean the ignition, but ignition was related to the adverse weather event. I'm not going to explain too much details, but it was related to La Nina activities. And then because of La Nina activities, they formed kind of high pressure over here and low pressure in the south of California. And because of this, they generate very strong easterly wind in the California region. If you know a little bit about American map, here in Nevada, they are relatively dry area and desert. So air is already dry, but we also have Rocky Mountain here. So if air moves along the mountain, it also warms up faster due to the compression. And this strong wind ignited the fire and also acted to spread the fire much faster. So it was the major occurrences of the massive wildfires. But this type of compound hazard is more dangerous because it influences people's perception. For example, if you are suffered from so long rain and thunderstorms or humid conditions, you may not worry too much about dry conditions, right? So this kind of compound hazard make people unprepared for next hazard. But here in this side of the world, like Hong Kong, we are caring more about moisture, right? We are suffering more from the moisture. And in this moisture, especially when we have a heat wave event, our body sweats. And then through the evaporation of the sweat, our body naturally cools down the body temperature. So this is a natural system. But imagine that you have such a high humidity surrounding you, then your sweat will not evaporate effectively. So that's why, even with the same temperature, as humidity increases, their impact on human becomes more severe. And if you look at the global trend of dry heat wave and moist heat wave, you can clearly see that in the South China, along the coastline, we are actually having significant increases in the moist heat wave during the last 60 years, as well as South China Sea. So we have to care more about health impact of this moist heat wave. But where this moisture comes from? If you look at this map of global total precipitable water, we are in the western side of the world. We are having more moisture because of warm water compared to the eastern side. And then there are also more moisture in the tropics. Ocean has much more moisture than the land because it's evaporated from the ocean directly. But if you look at the movement of the moisture, this determines the weather in the places we are living. So the water can be transported from ocean to land by monsoon system like this, or tropical cyclones, or some kind of easterly wave, or some filament-style moisture transport. This is called atmospheric river because it looks like a river. But how climate change, how global warming influence rainfall and moisture? Most of them can be explained by simple physical theory called Clausius-Clapeyron equation. We all know that water vapor can exist in the three different forms: ice, water, and vapor. But if you think about these two, water and vapor, as temperature increase, atmospheric water vapor holding capacity increase by 7%. So it's exponentially increasing. In other words, if temperature increases, it determines the maximum ceiling of how intense rainfall can it be, and then how rapidly evaporation happens. So, in the warming climate, somebody called it atmospheric sponge effect. Because atmosphere can hold more, it becomes thirsty, so it holds the moisture like a sponge. And then this kind of phenomena actually lead to the rapid intensification of hydrological cycle, and ironically, it increased floodings as well as drought and wildfire. I'm going to explain you further. So, globally, and on Earth, the water vapor is recycled. It remains back to the ocean. It is typically evaporated from the ocean to the atmosphere directly by evaporation, or sometimes through the tree leaves. This is called transpiration. And then once they move upward, they condense and then form a cloud. And then when cloud has enough moisture to hold it, they precipitate out. And this precipitation will move back to the ocean by surface runoff or groundwater flow. So this entire cycle is called hydrological cycle. But if you remember the global warming pattern, we have learned that land area warms much faster than the ocean. So on average, global land temperature has been warmed about 1.59 degrees Celsius, whereas ocean has been warmed about 0.88 degrees Celsius. So it's almost twice larger. And then because of that, land relatively forms a low pressure, and then ocean relatively forms a high pressure system. And then that impact changes in wind direction from ocean to the land. But at the same time, land has been warmed faster. So due to the atmospheric sponge effect, the soil moisture will be evaporated easily. So it is always remaining as a dry condition. But once moisture is transported from the ocean, it will make very intense short-term rain that actually provide challenges in the water resource management. For example, in current status, let's say we have 10 millimeter per hour precipitation every day. 10, 10, 10, 10, 10. But in a warmer climate, it will be more like this. 0, 0, 0, 0, 50. So on average, it will be similar, but it will make in a form of short-term and very intense rainfall. But on top of it, urbanizations and an industrialization in the Great Bay Area pushes more into this phenomena. For example, if you look at this map, compared to 2 decades ago, where most of the land are yellow color, which is farmland, and then now it becomes red color, which is built-up area. Built-up area means that surface is paved by asphalt, black asphalt. That black asphalt absorbs the radiation during the daytime and release it during the nighttime. And that is why, if you look at the thermal camera of Hong Kong, even during the nighttime, the residential commercial area have much hotter temperature than surrounding climates. So this effect is called urban heat island effect. And then along this island industrialized area, we have much hotter temperature and much stronger precipitation and relatively weaker wind speed. Are we observing it? Yes, there is a clear evidences. So this graph is from Hong Kong Observatory of showing the hourly rainfall record from 1884. So you can clearly see, this is measured during last 140 years using same instrument and same places. And as you can see, it took about 40 years to break the record earlier. Another 40 years, 26 years, 14 years, and 2 years. What you can see is that the record has been broken so dramatically, it's keep increasing. So 1 hour precipitation has been keep increasing, and rate of breaking the record has been accelerated. So this is a clear evidence of accelerated hydrological cycle. Same is true in the United States. So this figure shows the daily maximum precipitation, and you can clearly see the increasing trend of our daily precipitation. So globally, we are actually experiencing more intense short-term rain. So what we have to focus on is not an average. We have to focus more on short-term, intense, extreme rainfall. According to the World Meteorological Organizations, they investigated the number of deaths by natural disaster every decade by different types of natural disasters, and then reported economic losses. And as you can see, except for this, a lot of fatalities in early 1980s by drought in Africa, majority of them are light blue color, which is a storm, and specifically it's tropical cyclones. And if you look at closely, during last 3 decades, number of deaths by tropical cyclone has been decreased. It's a good sign. It's partly because of the development of early warning system and development of the city infrastructure. But if you look at the global economic losses, it's a different story. It's keep increasing, right? And recently, during last 2 decades, number of fatalities by extreme temperature, specifically heat wave, has been increased. And now it become the dominant factor of fatalities by natural disasters. And then also, second largest contributor of the economic loss is by floodings. So the lesson here is that now we have to care more about death related to the heat, and we have to care more about money losing by flooding or rainfall-related disasters. But let's move to one of the most devastating phenomena called tropical cyclone. So people in Hong Kong are quite familiar with the tropical cyclones, right? These tropical cyclones are formed over the warm water, and then it's cyclonically anti-clockwise rotating in the northern hemisphere. But if you look at the vertical cross-section of this structure, the air is actually moving inward using in this spider shape, and as it moved inward, it gained more velocity, it gained more wind speed by angular momentum conservation. And near the I-war region, in very thick thunderstorms, it has upward wind and then it goes outward. So typically in outside of 500 kilometers from the center, there is a subsidence wind. And because of these unique structures, you have several layers of thunderstorm. It gets stronger, and then wind speed gets stronger as it closer to eyes of the tropical cyclones. So that's why many of the damages are associated with the wind and floodings. But also at the same time, especially on the right side of tropical cyclone, it pushes the water from ocean to coastline. And that's why it also generates storm surges. So on top of the sea level rise, storm surge is another concern. But I brought this slide because it can be useful for people living in Hong Kong. And because of unique geographical structure of Hong Kong, the location of their making landfall is actually matters a lot. So typically, when tropical cyclone move this direction, the right semicircle is called dangerous semicircle, where we have relatively stronger wind. And on the left side, it's called navigable semicircle, relatively weaker wind and more precipitation. But in the places like Western North Pacific, this tropical cyclone typically move along the subtropical ridge. And that's why the right side has a more packed structure that further strengthens the wind speed. So if we are located in the right side of tropical cyclones, the wind comes from southwest, southeast, and then left side wind comes from northwest because it's counterclockwise rotation. But at the same time, right side, we have more stronger wind and then more storm surges because it pushes. And then on the left side, it has heavier precipitation because of the deceleration of the airflow. One of the brilliant example was in Typhoon Hagupit in 2008 and Typhoon Chantu in 2006. Both of them recorded similar lifetime maximum intensity, and the location of landfall was also kind of similar. But Typhoon Hagupit made a landfall on the west of Hong Kong, which means that Hong Kong is located in the eastern side, so this semicircle. And then this one, Chantu made a landfall on the east of Hong Kong, so Hong Kong was located in the left semicircle. So if you look at the wind speed during the landfall and storm surges, Hagupit recorded much higher wind speed and then also much higher storm surges. So people may consider that, oh, maybe it will be better to have a landfall on the eastern side. That can be true for wind speed, but not true for air pollution. So according to my recent study in my group, we divided the tropical cyclone into two groups, one in the eastern side, one in the on the western side. And then we tried to understand their impact on air pollution. Do you sometimes also remember that air pollution becomes intensified when tropical cyclone approaches? This can be true or false, depends on the location. So what we found is that when tropical cyclone is located in the east of Hong Kong, it brings northerly wind and transport of air pollutant to the Hong Kong area, and then with a very strong subsidences that traps the air in the boundary layer, the air pollution can be increased by 93%. But on the other hand, when tropical cyclone is located in the left of Hong Kong, it brings relatively clean air, clean sea air from the south, and that's why, because of the clean air and then precipitation, it drops the air pollution by 40%. So it's a different story. Where they make a landfall really matter. And it's actually because of Hong Kong's unique location. But what is a more alarming concern is about tropical cyclones' residence time over land. For example, in 2024, Hurricane Helene made a landfall, and then it it penetrated further inland all the way to the North Carolina. And then that generated massive inundation in the North Carolina. But also in Hong Kong, Typhoon Haikui in 2003 survived a longer time over land, and then that was the major contributor of the record-breaking rainfall in 2023. So scientists want to understand why they are surviving more over the land. And then based on climate model experiment, what they have found is that if surface ocean temperature is warmer, they survive longer time over land. And then when they artificially remove all the moisture out, the decreasing rate is almost the same. In other words, warmer temperature provide more moisture into the storm, and then that storm can survive much longer time over the land. But at the same time, there is a consistent consensus that relative proportion of major hurricanes stronger than 50 meters per second has been increased during last 40 years, and then it is expected to increase in the future. But regarding the future's projections, we have to rely on climate models, and then to understand the future change, climate scientists globally, collectively, collaboratively, publishing a report after the establishment of Intergovernmental Panel on Climate Change, IPCC. And then every 6 years or 7 years, they publish a report with more evidences, with better techniques, or with higher resolution data. But still, currently, the climate model is around 100-kilometer resolution, and it is not enough to capture small-scale phenomena like cloud or radiations. But if somebody asks me how reliable are climate models, I want to answer that climate models are remarkably reliable in terms of temperature predictions. So just as you can see in this graph, the climate model captures very well about their global temperature trend, even in the fourth assessment report. But in terms of extreme weather events, such as sea level rise or Arctic sea ice extent, climate model is underestimating the observations, and then also the Arctic sea ice has been melting much faster, but climate model do not accurately predicting it. So there are some challenges and uncertainties, especially about extreme weather event and regional climate details, but mostly it works in a way to underestimate their extreme event. So to improve the accuracy of climate projection in the future, I am also participating in the international collaboration of conducting a storm resolving scale simulations. So here is one example of snapshot simulations. One snapshot of the climate model simulations. And as you can see, the tropical cyclones, it looks like satellite images. So now we are resolving more detailed structure, but still this is not enough. But this gives an idea that what we know and what we don't know, what we still need to figure out. And lastly, due to the development of artificial intelligence, it provides a cost-effective way of predicting the extreme weather event. So here is one study just accepted, not published yet. It will be published maybe this week or next week. So we tried to challenge one of the long-lasting problem of tropical cyclone intensity prediction. And then here in this model, we found the 25 to 38% improvement in the intensity prediction. But our philosophy is that AI model should not be treated as a black box. We should totally interpret why it has an improvement, why it doesn't have improvement, what is the compensating factors, and so on. So if you're interested in, I will be happy to share my paper. In the Climate Extreme Laboratory in City University of Hong Kong, where I am leading, our mission is to improve our physical understanding of extreme hazard, and then also improve the climate predictability using cutting-edge high-resolution climate models, theoretical approaches, and innovative AI applications. So let me conclude. Here is the take-home message. Climate change is not generating new phenomena, but it intensifies extreme weather events by increasing its frequency, duration, and severity of existing events, but in a way that we have never experienced. So that's why modern infrastructure and agriculture systems designed under the historical climate condition lack the resilience withstand these unprecedented climate extremes, and it will be severely tested by continuous warming. That's all of my talk, and thank you for your attention.